Uh, there is one useful theorem that related a moment of inertia calculated through the center of mass with the moment of inertia calculated by any point through an axis that is parallel to this initial axis. So we calculate I passing through the center of mass, and we wonder what is I if now is passing not through the center of mass, through a point P. If we are calculating a center of mass through this axis, the object is rotating in this way, like this. Every point is rotating around the center of mass. Okay, every point, this point is rotating about the center of mass. But now, if we make I through this point P, every point it will rotate through the center of mass like this. So we try to understand how to relate the I through a parallel axis, the moment of inertia through a point P. We want to relate it with the moment of inertia to the center of mass. And the relation is that once that you calculate the moment of inertia to the center of mass, the moment of inertia through another axis that is parallel is the one that you have calculated through the center of mass plus this quantity. And the proof is here. This is the proof. Let's say that you are in this axis. So there is an axis here that is coming to your eyes. There is another axis here that is also coming to your eyes. They are parallel axes. So when you calculate the moment of inertia through the point xi through the center of mass, you are calculating m by this distance square. But this distance square is xi squared plus yi squared, and this is the distance square. So I center of mass will be the mass m sub I multiplied by the distance square between the axis and the point, and the distance square between the axis and the point is x sub I plus y sub I squared. So this distance that we have put is the distance that is perpendicular to the axis. This distance, if you see the axis coming to your eyes here is the axis coming to your eyes, the body is rotating around the axis. This distance is the distance that is perpendicular to the axis, and xi squared plus yy squared. So let's go to relate this amount, this quantity, to the inertial moment if we calculate through this point P through an axis that is parallel to this axis. So imagine an axis going to this point P, going to your eyes, parallel to the axis that is passing through the center of mass. And we are going to prove that the moment of inertia through the point P, through this point P, is the same moment of inertia to the center of mass plus this quantity m by the distance d that separates the two axes, d squared. Okay, let's go to prove it. Well, this is the proof. When you calculate the inertia, the moment of inertia to the center of mass through this point M, through this point center of mass, you calculate the mass by this distance square. Let's go to call this distance square Ri. And so Ri square is simple. It's true that is xi square plus yi squared. So this is the point mi, this is the axis that is coming to your eyes from O, and this is the parallel axis that parallel to this axis that is going from the point P and this is the axis, and we want to calculate the moment of inertia of this body that has one mass but many masses. Later we will sum for all the masses. This moment of inertia that is going through this axis, parallel to this axis, going to a point, an arbitrary point P on the body. So the moment of inertia from this point P will be the mass mi by this distance, but this distance in red, is xi is r prime squared. Let's go to call this distance r prime. So this is r prime squared is xi minus a squared plus a yi minus b squared. So the I over calculating over the point P, it will be the sum of the mass mi by the distance, by this distance, xi minus a squared plus yi minus v squared. Okay, so if I put the number I sub p here, I sub p is this quantity, the same quantity that I write here. And I developed all this quantity. I have 4 terms. If you develop, you will find 4 terms. The first term will be I center of mass, because this is x sub I, y sub I. X sub I is the x sub I squared plus y sub I squared is r squared, is the distance squared from the center of mass. So if I make the sum, this is the E sub P, E sub center of mass. So it will be I. If I make the sum now, I will make the sum for all the points. I will have m sub I, the sum of m sub I by x sub I squared plus y sub I squared. And I said that this calculation will be the calculation when I will do it through the center of mass. Of course, it will be n sub I by r sub I squared, because this quantity is r sub I squared, plus a squared plus b squared. A squared plus b squared is the separation between the two axes, so it's d squared. D is the separation, and the sum of m sub I is m. So I almost have proved that the inertial moment through the point P is the initial moment through the point P is the initial moment through the center of mass plus m by d squared. But there are 2 terms. When I make the sum here, and I make the sum, I have to prove now that the sum of m sub I, x sub I equals 0. And the sum of m sub I, y sub I equals 0. Why? And the reason is that x sub y is the distance from the center of mass. And y sub I is the distance from the center of mass. And why this sum have to be 0? I'm going to prove you now. Okay. Let's go here. The sum of xi plus xi is 0. Okay? So this is a quick proof to get the taste why the summation of m sub I by x sub I, when you sum it's 0. Yes, a very, very brief when you sum to all the particles, and when x sub I is the distance from the center of mass. Okay, this sum is 0. Yes, to make a very, very easy example. So suppose that you have 2 particles, but you can put n particles. Suppose that you have the first particle, x1. Let me call this axis the axis x prime, okay? So suppose that you have an x prime, the mass m1 is 1 kilogram, and you will have it on the position x prime equal 2 meters. x prime equal 2 meters is the first mass, the second mass is at the position 8 meters, and the mass is also 1 kilogram. You can put any amount of mass here, It will make, if you put more mass here, it will mean that the center of mass, instead of being here, it will be more near this mass. If you put more mass here, the center of mass will be very near of the mass. So what I want to prove you is like this. If you calculate the center of mass in this, with these numbers, the center of mass is defined the mass by the distance plus the mass by the distance divided by the sum of the mass, or the total mass by x prime of center of mass. If you take this is the total mass by the center, by the position x of the center of mass equal m1 x prime 1 plus m2 x prime 2. So let's go to calculate x prime center of mass. X prime center of mass will be the mass by x prime 1, 1 by 2. The distance from the origin is at the position 2, plus m1 by x prime 2, 1 by 8, divided by the sum of the two mass. So the center of mass is, like we imagine, is at the middle between the two mass. Okay? It's exactly at the middle. 1 step, 2 step, 3 step. 1 step, 2 step, 3 step. What does it mean that? It means that the center of mass is the center of the mass. All the mass is the same quantity of mass is to the right that to the left. This is the meaning of a center of mass. The center of mass is here because you can find so many mass dispersing the distance to the right as so many mass dispersing the distance to the left. So this is the center of mass. Now, suppose now that I want to calculate from this point, from the center of mass, the position of the center of mass. So if I want to calculate the new center of mass from the center of mass, I'm going to calculate m1 by x1 plus m2 by x2. So m1 will be 1. x1 will be minus 3 because he's from the center of mass, he is at minus 3 meters. Plus m2, which is 1, m2, which is m2, that is 1, m2, that is 1, plus the distance from the center of mass. The distance from the center of mass is plus 3. So this will be 0. So x center of mass will be 0. So m1 plus m2, that is the sum of the mass, the total mass, the sum of the mass, the m1 plus m2, etc., the mass by x center of mass would be 0. And this is the equation that we have. Good. So we have proved the same thing happened for y center of mass. The sum of m sub I by y sub I is 0 because we are at the center of mass. I hope this proof is enough. It's easy also to prove it in a general way, but it's not necessary. Just catch this idea, but it's very easy. It's just to put x prime here, x prime I, to put x sub I minus a. Doesn't matter. Go ahead. And the homework that I want to make you is very easy. Is first of all, you imagine that you have a ring, just a ring of mass m. This is the ring of mass m. Okay, this is the ring of mass f, radius r. Let's go to put the radius r here. Okay, radius r. So you have the ring, and you have an axis that passes through the center of mass. This is the axis that goes to your eyes. If you see from here, it will go the axis through your eyes. Look at in the picture. This is the axis, and this is the ring. Okay, this is the ring. So you calculate the moment of inertia of this ring. It's very easy to calculate. I think that I've already calculated in another video, I think. Okay, now I want you to use the theorem of the parallel axis to calculate the moment of inertia of the same ring that is rotating not through this axis, through a parallel axis that doesn't pass through the center of mass. It's a parallel axis that passes through the point P that is tangent, is a distance r from the center of mass. Okay, this is the homework. To find I sub p is easy. I sub p is I center of mass plus find this and find what is here. Okay, good luck.